Okay, so this centripetal force, let's have a sort of look at it in action. If you imagine this truck, we can change three things about this truck moving in a circle. We can change the speed of the truck, we can change the mass of the truck, and we can change the radius that the truck is travelling in. So if we just adjust one at a time to make things nice and simple, the thing that you need to look at is the size of this arrow. Now this arrow is directed towards the centre of a circle, so it's showing us the direction of the force, so the centripetal force is towards the acceleration, and you need to keep an eye on the size of the arrow. So if we make the truck go a little bit faster, so we'll go up to here, then you can see on the diagram the truck's going faster, and if you notice the size of this arrow has increased. So we know that the faster you go, the larger the centripetal force that acts on you. Kind of makes sense, because if you imagine you're on this truck, you're going to feel as though you're being flung outwards, which is always a little bit confusing, but the force on you is trying to pull you inwards. So because this centripetal force is pulling you in, you feel a little bit as though you're being flung outwards, but the force on you is actually inwards. And you can see from the size of the arrow, if I decrease the speed of the truck, then the arrow gets much smaller. Okay, so if we set that back to where we were, let's now take a look at the mass of the truck. So if we fill the truck up, so if we do that, the truck gets full up, and you can see the arrow has increased again. In case you missed that, let's make the truck nice and empty, and it's a small arrow, and if we make the truck full, then the arrow gets much bigger. So the more mass you have got, the more centripetal force you need to keep you moving in a circle. This idea you can probably think of if you fly something around your head on a string. If that thing that you fly around your head on a piece of string is more massive, then that's going to sort of pull on the string a lot more, so that centripetal force is going to be bigger. The final one, which is maybe the hardest to get your head around, is what we call the radius. So again, if we increase the radius, let's make the truck go right round the edge of this circle. There we go, so the truck's now moving right round the edge of the circle. We can see that the arrow is tiny, so the larger your radius, the smaller the centripetal force. Whereas if we now make the radius really, really tight, so you can see from there, very, very tight radius this truck's now going under, going around the circle, and you can see that our arrow is large. So the tighter circle that you turn, the more the centripetal force acts on you. If we just look at the theory, why does the centripetal force depend on mass? Well, if you remember from Newton's second law, force is proportional to mass. So if we increase the mass, then we would increase the force. So the greater the mass of whatever that's going in circular motion, here I've got a ball being flung around on a string like we did in lesson, the greater the mass of the ball, the greater the centripetal force. That's sort of quite a simple relationship there. Let's now look at speed and radius. Well, again from Newton's second law, force is proportional to acceleration. So if you change the acceleration, if we keep the mass constant, if we change the acceleration, we're going to change the force. Now if the ball goes faster, then the faster you go, your acceleration is increasing. So the faster the ball, the higher the acceleration. So if we make the acceleration higher, we make the force, or the centripetal force needed, higher. So there is a greater centripetal force. And the other one, which as I say I think is always maybe the most confusing, if we make the radius smaller, think about how much it changes direction. It's changing direction in quite a tight circle. So that tight circle means it's changing direction a lot or more quickly, so its acceleration is much greater, so the greater the centripetal force needed. So the greater the speed and the smaller the radius, the larger the centripetal force needed to maintain circular motion. Some of the examples, a car travelling round a bend. I wonder what the force is. Well, the thing that's keeping that car moving in a circle is the friction in the tyres. Without the friction in the tyres, the car would not be able to go around a bend in a circle. It would just skid off into a straight line. If you're whirling a stone round your head, or a ball like we did in lesson on the end of a string, well, the thing that's providing the centripetal force is the tension. you feel a pull in the string. So a planet moving around the sun. Here there's no contact, is there? The planet's not on a piece of string, the planet's not rolling on a surface, so there's no friction or tension, but there is a gravitational pull from the sun, and that gravitational pull keeps the planet moving around the sun. Finally, an electron orbiting the nucleus. Again, if you think back to year 10, we know that the nucleus of an atom is positive and the electrons are negative, so we've got some kind of an electrostatic force between them. We've got the positives attracting the negative, so all very sort of easy to hopefully understand examples of centripetal force.